Okay.
Hi, we are Team Plastic Free Willy, and let me start by introducing the problem by telling you about the biggest mass poisoning event in British history. It all started when a chemical plant accidentally dumped some pollution into the local reservoir, which was the only source of fresh water for the entire town of 80,000 people. Because they had no way of cleaning it up, they just had to roll the dice and hope that it would be okay, hope that the people wouldn't get as poisoned as they potentially could have been. But they were wrong, and thousands of people were killed, and tens of thousands had long lasting damage from it. And all of this could have been avoided if we had an easy, scalable way of cleaning up any pollution on demand. Now, this isn't just a one off issue. Reservoir cleanup is a big untapped market. It's a $4.6 billion market around the world, and it's growing at 8.7%, which is quite rapid. Now, the most of this market is filled by large stationary pollution control for known pollutants. There is big demand for the sort of pollution control that we talked about on demand for any sort of plastic, and this can be differentiated by something that's cost effective, obviously usable to clean up any sort of pollution, and dynamically deployable at any time without needing heavy machinery. And that's exactly what we built. Free Willy is easily deployable en masse to clean any type of reservoir pollution. And the basis of this is an off-the-shelf sea scooter. This is our propulsive system, and mounted onto this are our proprietary filtration and control technology. Because it can be so easily mounted on, this means that any sort of filter that we want to put on can be easily swapped out, which is 6 screws, to deal with any sort of pollution threat. Now, let me talk a little bit about our filtration design. We have 2 filters on there that combine to filter 22 liters of water every second, and we designed the geometry of it so that we can make sure that large particles don't get clogged in the filter by creating angled inlets that deflect these particles away. Now, this was designed with a lot of validation and testing, both with computational fluid dynamics simulations as well as prototyping and real-life experimentation. Finally, let me tell you about our centrally mounted airbox, which contains all of our electronics. It's rated to be waterproof up to a depth of 1,000 meters, and it's mounted in a spot so that it provides passive roll stability to keep our vehicle stable in even rough waters. Additionally, we have 2 thrusters that provide 6 pounds of thrust and give us attitude control in addition to the actual propulsive control that comes from the off-the-shelf sea scooter.
Taking a look at our system diagram, we can divide our project into 3 main components. The vehicle with the filtration and control packages, the communication system, which communicates all the data collected by the vehicle back to an Amazon Web Services platform, and then finally, the mission planning and tracking control, which uses several of our proprietary software to control the vehicle and execute missions. Looking more specifically at the block diagram, we can break the vehicle down into the vehicle control involving using several sensors and control actuation, and then the filter system and the filtration system control. Then we have the user interface, which is composed of the computer vision software that we use to control the vehicle, and then the path and trajectory planning to plan and execute missions. And then finally, we have the overall dashboard, which collects data and allows us to analyze real-time mission data. In designing the electrical floor plan, we had several key floor plan requirements that have to do with the way that the vehicle constrains our ability to design. Most importantly, we have limited unit dimensions, and even within these unit dimensions, most of the space is taken up by the vehicle itself. We also need to be able to support autonomous and remote control, which is very important in order to be able to execute large missions with a number of these vehicles. And we need to be able to support field data collection. This is an extremely important thing to be able to support for pollution control so that we can determine what kind of pollutants are present and what kind of filters are required to remove them. Then on top of that, we also have a battery restriction, which is related to the size restriction. And we need to be able to support a sufficient speed in order to get the volumetric flow rate required to have a sufficient amount of pollutant filtering capability. In order to implement this floor plan, we designed a PCB that uses the primary propeller of the sea scooter, and then it adds various different control surface abilities and data collection abilities in order to control the vehicle. For example, we add ESE brushless motor control for the additional propellers. We have a magnetic control system which hacks into the sea scooter in order to control the main propeller. And then we have our particle detection system, which we implemented for a microplastic realization of the vehicle. In order to do this, we had to hijack the full capabilities of the Raspberry Pi's GPIO. because the Raspberry Pi, it has limited space, but we also wanted to be able to control this with a single microprocessor given our space requirements. And as you can see, we implemented this design on the PCB to the right, which easily fits within the dimensions of our airbox space available.
So to make Free Willy easily deployable, we built a number of software packages to help automate our system. We designed a robust trajectory planning algorithm for our robot. And using the system is relatively simple. All the user needs to do is input a PNG and world file of a reservoir they'd like to clean up from OpenStreetMaps. And the system converts that PNG into an occupancy grid via computer vision, and then plans on that grid via a sweep algorithm we adopted from Atsushi Sekai, a Japanese roboticist. The system then localizes that generated path with information contained in the world file. And to get the robot to actually follow plan trajectories, we developed a robust control package. The goal of the control package is to allow the robot to follow plan trajectories with 1 meter accuracy. And to do that, our control packages consist of a sensor fusion algorithm running off of a Kalman filter, a PID controller, and a control actuation script. The Kalman filter fuses IMU and GPS data along with a robust physics-based prediction step to reduce sensor noise. And the output of the Kalman filter is fed into the PID controller, which combines it with the desired trajectory to generate control outputs. We also created a dashboard to allow users to track Free Willy while it's deployed. And the dashboard displays data coming off the vehicle at a frequency of 1 data packet for every 10 minutes. And to get data to the dashboard, the vehicle transmits over BLE to a communications buoy, which forwards the data via cellular transmission to AWS. We built an AWS pipeline to store that data and display it on a dashboard. So far, we've covered how Free Willy works as a system touching on the vehicle design, the electrical hardware, the communication system, and the user interface. Let's talk a little bit more about how we hope that Free Willy will be deployed. And deployment of our system poses a number of challenges. The first is that while Free Willy captures pollutants, it doesn't actually destroy them. So with that, organizations using Free Willy need to have in place robust procedures to deal with pollutants. Negligent actors may simply just move pollutants from one reservoir to another body of water and not actually get rid of them. The second challenge is the fact that since Free Willy is made out of plastic, it will begin to decompose while it's in water. We believe that while Free Willy is operational, it's going to be able to pick up a lot more pollutants than it produces. However, that being said, organizations using this need to have robust collection procedures to collect inoperable Free Willy vehicles. We've covered the system diagram, we've covered the system, and we've also covered some of the use cases of the vehicle. And we'd like to open it up to any questions you might have.